Now that we have everything we need, we have our optimization equation as well as our constraint. We have two variables, just x and y here, along with two equations. We're going to manipulate the constraint equation, all right, get it down to one variable or one variable by itself so that we can plug it into the optimization equation and work our way through the problem using only one variable, all right, so that we can get to the answer that we are seeking. Right? So you'll see that I started to isolate the y because it would be definitely the easier one in the constraint equation to get by itself. All right, so I subtracted the x squared over, then divided the 4x over, and I'm left with y is equal to 1,000 minus x squared over 4x. All right, the whole reason for doing that again is to plug that constraint equation into my optimization equation. All right, so you'll see it's x squared y. I am now going to replace that y with what I came up with in the constraint equation, which is that it's equal to 1,000 minus x squared over 4x. And when I do that, it looks like this. And you'll notice now everything is in terms of x. I'm dealing with one variable. Okay, so I'm down to one equation, one variable, so I can work through and optimize, or in this case, find the critical values that I need to be able to optimize the volume of this box. Okay, so I go through, I simplify a little bit. This x squared, one of the x's with that can cancel with the x on the bottom here, and then I distribute the x to the top, so this becomes 1,000x minus x cubed over 4. All right, that 4 on the bottom belongs to both of those terms. So 1,000 over 4 becomes 250x, and then I just turned this into 1 over 4x cubed so that it's in an easier format to do my derivative, and in this case, the power rule. All right, so I'm going to go through and do the derivative of that so that I can find the critical values that I need. The derivative of that, which is here, 250 minus 3/4 x squared. 0 is equal to that, right? Because I'm trying to find critical values here, maxes and mins. So I'm looking for those locations with tangent lines, slope equal to 0. So set it equal to 0. Solve it for my critical value. In this case, approximation, because I had to round, it's 18.257 feet, all right, as the x dimension on this box. Okay, so I just have to verify. I come back up here, all right, and just want to verify that that is an actual maximum location with my number line and testing my points in the first derivative. So I did f prime of 1 and I got a positive. I did it because that's between 0 and 18.257. F prime of 20 gives me a negative. All right, so clearly, again, I am coming up to this 18.257, increasing as I get close to it. And then when I get there, all right, I hit that plateau, and then I'm decreasing after it. So what I'm doing there is, or what I have there is an actual maximum value, all right, or maximum location, all right. And so 18.257 is the location where I would be hopefully maximizing my volume, all right. So in this case, I know to use that as my x. I just now need to find all of the dimensions, all right. So I need to find the y. How do I do that? Well, I have from this here, I have that y is equal to 1,000 minus x squared over 4x. So I can plug in my now found x location, all right, plug that dimension in. I end up with my y dimension being 9.129 feet approximation, right, because we rounded a little bit, all right. And so I now have the three dimensions that I need to maximize my volume, all right. So there's two, remember, there's two x dimensions. The bottom was a square, so I have x times x. So that's 18.257 by 18.257. And then my third dimension being the y that goes up, that up dimension there is that 9.129 feet. So there are my three dimensions. That's what they were looking for. If I wanted to find my actual maximum volume, I could just multiply those three dimensions together. Having those dimensions, all right, for this would give me my max volume, 3,043 cubic feet. All right, so I just optimized based on the amount of material I was given, okay, which is 1,000 feet squared of material. I can optimize using those dimensions and get a volume, a maximum volume of 3,043 cubic feet. In example 4, they're asking about a cylindrical can that's open at the top, and it needs to hold 500 cubic centimeters of liquid. That right there, that number, anytime you're given that number there, that should key you off as to what your constraint is for this problem. In this case, I need to be able to hold 500 cubic centimeters of liquid. Okay, that can that we are constructing, all right, that we are optimizing here has to hold that amount of liquid. So what they want me to do is find the radius and the height, so the dimensions of this can that minimize. Now we're minimizing the amount of material needed. So basically think about a company that wants to make sure that they're using the least amount of materials possible to make their cans to put something in. If they're using less material, then obviously they are spending less money, and they want to make sure that they're fitting the most amount of stuff in that material. Okay, and in this case they have to fit 500 cubic centimeters in that thing, right, and what in the can that they're making. All right, but they want to do it by using the least amount of material. Okay, so that's what they're looking to do here. So I set it up, I labeled the can that's already there. My optimization equation, again, I'm looking for the least amount of material. Material and surface area are essentially the same thing because that material covers the outside area of that can. Okay, so I have my equation for that, and that's basically just adding the surface areas together of all the components of that can. I have pi r squared, that's the area of the bottom circle of the can. Notice I did not include the top because it said at the beginning that it is open at the top. The 2 pi rh is, remember, 2 pi r is the circumference of a circle. So we have a circular can here, right? The 2 pi r covers the distance around the can, and then the dimension going up, the h that's labeled there, that's represented there. So 2 pi rh, all right, covers the surface area of the outside of that can. All right. And then what is my constraint? We talked about that. It's 500 cubic centimeters of liquid. So what is the formula for the volume of a cylinder? In this case, it's a cylindrical can. All right. It's pi r squared times h. So pi r squared being the area of a circle, right? So that's my two dimensions, area of a circle. And my third dimension comes from going up with the h, right, labeled on the can there. So pi r squared h. All right, and just like we did before, we're going to take one of the equations and plug it into the other so that we are only working with one variable. All right, so you'll notice from my constraint equation, the easier variable to get by itself is the h here, so I did that. I just divided the pi r squared over, and I'm left with 500 over pi r squared. And then I plug that into the surface area equation above, okay, the optimization equation. Instead of the h there, I replace that h with the h that I came up with here, which is 500 over pi r squared. Now all I have is nothing but r's. All right. The rest, all the way down to here, is simplifying. All right. So I just multiplied that out here. Okay. And I end up with pi r squared plus 1,000 over r. I rewrote it in a way that allows me to do the power rule because, again, I'm finding critical value, so I need a derivative. So I take the derivative. It's 2 pi r minus 1,000 r to the negative 2. Set that equal to 0 to solve for r and get my critical r value that I need, all right, to minimize this, all right, and from there, going through and solving to get r, the approximate value of r, because it turns out to be a decimal in this case, all right, did some common denominator stuff here, some algebra stuff to get to the point where I'm at 2 pi r cubed minus 1,000, okay, 1,000 is equal to 2 pi r cubed, and then solve for r there, and I get 5.42 as my approximation. All right, 5.42 centimeters as the radius. Okay, so remember, I'm trying to minimize surface area. So minimize would mean minimize these dimensions. So I have to test and see that 5.42 is an actual minimum value. How do I do that? Again, my number line with my first derivative to see that I'm going to be decreasing to increasing. When I did that, I tested a point between 0 and 5.42, and I got 1, or I used 1, and I got a negative number there. So that means I'm decreasing as I approach 5.42. All right, I'm coming down this way. And then as I come out of 5.42, I tested a point, and that's 6, and I'm getting a plus there, so it's increasing. So clearly in this case, I have myself a minimum at 5.42 will help me find the minimum surface area. That'll be the radius at the location where the minimum surface area occurs. All right. So now the next step will be to find the actual height that goes along with that radius. All right. So then finally find the h using the h equation that we came up with before over here. All right, so I know that h is equal to 500 over pi r squared. So I'm going to plug in my newfound r, my radius for my minimum, and then plug that in, and I end up actually getting the same number, right? So they end up being the same, the radius and the height. Okay, and so they're the dimensions that I need to minimize the surface area of this can, use the least amount of material possible to still be able to hold that 500 cubic centimeters. All right, so they're my dimensions. And then in order to find the actual minimized surface area, I use those dimensions and just plug in the R and the H into my surface area equation that I originally set out as my optimization equation. Plug those in, and when I put that in the calculator, it ends up being 184.58 square centimeters, because we're talking about area here, of material that I would need to make this can to be able to hold the 500 cubic centimeters. Right, that's the least amount of material that I can use. All right.